we come to the last module of this presentation. Now in module 3 we looked at the implications of nonlinearity, which built on what we had looked at in module 2. In module 2 we had looked at the linear theoretical framework that was successful in explaining the observed seasonal cycle of circulation in the North Indian Ocean. Now our goal is actually to be able to simulate the observations as we see them, to be able to make predictions. So the question is whether understanding or insight is still important, and that's why in module 4 I'll deal with complexity and linearity, with prediction and insight. We've seen this before. The picture on the left is the wavelet transform at a period of around 3 years, averaged over time. So it's something like an FFT of the altimeter sea level. What you have in red is regions of high variability, in blue, regions of low variability. So we saw that a simple linear model, whose solution is shown on the right, is successful in reproducing the essential observed features of these minima. It produces them in the right places. And it turns out that given that it's a linear system, you can break it into pieces. Superposition is valid, and it allows us to understand that the minima occur because the effect of the Rossby wave is cancelled out by the local forcing in the locations where you get these minima. But we also saw that the solution in the linear system is much smoother than in the observations, and that a nonlinear system, a nonlinear model, is able to simulate the patchiness that you see in these minima, say of the west coast of India or of the coast of Oman. So the simulation is much more accurate in a nonlinear system. Unfortunately, however, it is the linear system that allows you to explain why it happens. And this nonlinearity is important because if you want to be able to simulate these chlorophyll filaments that you see in satellite data, there's no way you can do this with a linear model in which the chlorophyll would just drift offshore in a classical Ekman flow. That's not what you see in the observations, and you can simulate these filaments or squirts or jets seen of Oman using a nonlinear general circulation model run at a reasonably high resolution. This is at 5 kilometers. So this is something we actually want to be able to do, to be able to simulate what we are observing. And a nonlinear model is capable of doing that today. These chlorophyll filaments can be simulated fairly well with a high resolution general circulation model forced by observed winds. Now if you take a forecasting system, whether oceanic or atmospheric, the only way that reasonable accuracies are achieved is via data assimilation. The chaos that is inherent in such nonlinear and complex systems limits the forecast horizon. So after a few days, the model drifts completely from what is observed. And what is done in these forecasting models is to stop the model, to assimilate data which have become available, and to rerun the model from that point. So in data assimilation, the model is run for some time, say a day, before the model is corrected by assimilating new data that have become available. You assimilate the data, start the model again, make a prediction for some time, then assimilate new data again, run the model for some more time. That is how forecasts are made, weather forecasts or forecasts for the ocean. The problem is that the model state tends to drift away from the observations, and the assimilation of data constrains the model and limits its drift from observations. So a forecast actually blends observations and what the model tends to simulate. So in any model, the only way you get reasonable accuracies while forecasting is via data assimilation. But suppose you want to simulate climate. Let's say you want to make a prediction about the impact of climate change. You can't assimilate data when running a model for, say, the next 50 years. So your model has to be good enough. Your model has to be capable of producing realistic simulations, reasonably good simulations, to be usable for predicting the impact of climate change. So we need to know when a model fails, why it fails, and for that you need to know when a model succeeds, why it is successful. This understanding is critical if we are to trust models when we look into the future. Now this question of complexity does not necessarily imply complicatedness. For example, Lorentz could produce this strange attractor, the Lorentz attractor, which is a fairly complex three-dimensional attractor with these three fairly simple equations. Even simpler equations are known to exhibit chaos. So it's a question of complexity, not necessarily complicatedness. Let's get back to the East India Coastal Current and West India Coastal Current. What I showed you earlier were data based on ship drifts and hydrographic measurements. But now we have data from acoustic Doppler current profiler moorings that are deployed on the continental slope and shelf of the west and east coast of India. This map shows you the mooring locations in August 2018, and I'm going to show you some data from the west coast for the West India Coastal Current and east coast for the East India Coastal Current. So on the continental slope, from where I'll show you data, you have ADCP moorings. These are acoustic acoustic Doppler current profilers. So they send out an acoustic signal which reflects back from zooplankton, and this backscattered signal is used to estimate the horizontal current. So when you look at these currents, these moorings are deployed and they are serviced after a year. So you get continuous data every year, hour by hour, over a long period of time. And we have now had these moorings in place for about a decade. So this is the new look West India Coastal Current and East India Coastal Current. This is 4 years of data for the WICC and a similar set for the East India Coastal Current. Now you must remember that before these moorings were deployed, the only direct current measurements we had of the west and east coast of India were for industrially sponsored projects, and they were typically for just a few days or at best a month. So these ADCP data present an unprecedented, a hitherto unprecedented analysis of the variability that is inherent in the WICC and EICC. The red colors here show you poleward flow, and the blue colors equatorward flow on both sides. Now if you look at just 1 year here, from July to July 2009 to 10, you can see that it's not just a classical seasonal cycle. Even within a particular month, the current changes direction. That is of the west coast of India. Of the east coast, however, the direction change seems to be slower. So you could say that the seasonal cycle may be dominant for the East India Coastal Current, and the variability within a season or interseasonal variability for the West India Coastal Current. So suppose we ask a question. On any given day, say 19 September 2018, what would be the direction of the West India Coastal Current or East India Coastal Current? Now I could do this for any 19 September. I have data now for almost 10 years. So these ADCP moorings allow us to look at the variability in a way that we could not do earlier. What's plotted here in the black curve is the daily mean West India Coastal Current, and here the daily mean East India Coastal Current. The colored dots show you the direction of the current, the magnitude and direction of the current for each year. A particular color is for a particular year, and positive currents imply poleward flow, negative currents imply equatorward flow. Let's look at the EICC first. Even without averaging in time, you can see that during March to May, the direction of the EICC is almost always poleward. It's quite rare that you will get an equatorward flow. During the winter, during November, it's equatorward almost all the time. It's quite rare that you get poleward flow. But if you look at the West India Coastal Current, on the other hand, there is almost no day of the year in which you can't get either direction. There's actually none. It's only when you start averaging in time that the canonical seasonal direction becomes apparent. This is another way of saying that intraseasonal variability dominates off the west coast of India. So if you were to ask me what is the direction of the current today, I could hazard a guess for the West India Coastal Current only if I knew what was happening in, say, the last 10 days. But if I didn't know that, it would be tough to make a guess. For the East India Coastal Current, in many months of the year, I can make a reasonable prediction. These new data come with new challenges. This interseasonal variability is something we would like to be able to simulate, and models do have a problem there. But that's not all. If you look at just the annual cycle of the current of the west coast of India, you would assume that with the kind of powerful computers available today, it should be very easy to do that. But that's not true. What you see here is a depth time plot of the current of Goa. Red color implies poleward flow and blue color implies equatorward flow. So this goes from 2006 to 2012. It's about 6 years of data. And there are two things I would like you to note here. One is there are years in which the current was weak, the WICC was weak, that's 2006 to 8, and there are years like 2009 when it was strong. This is something we would like to be able to simulate. The other thing to note is that the phase is propagating upward. This color tilts to the right as you go forward in time. So there is upward phase propagation over most of the record, and there is downward phase propagation on certain occasions. That's another thing we would like to be able to simulate. The two panels below that show you simulations with state-of-the-art general circulation models. This one is on the Earth simulator. It gets the upward phase propagation right, but is unable to simulate the weakening during 2006 to 2008. The bottom panel shows you a simulation with data assimilation. It gets the weakening during 2006 to 8, but not the upward phase propagation. So even today, simulating just the annual or seasonal cycle of the West India coastal current is a challenge for the most powerful computers and the best of models. Now, simulation implies capturing as much of the system's complexity as possible. That's what we try to do in a general circulation model. Understanding, on the other hand, implies sufficient simplification to capture the essence of the phenomenon. So you try to understand what aspect of the physics or the science is driving or is responsible for what you are seeing, and try to simplify the model to capture just that part. That is what Lorentz did with her simple equations to describe convection. This gap between simulation and understanding was discussed in a highly perceptive essay by Isaac Held in 2005. Held says that the practical value of simulation is undoubted. You can make a prediction, and a prediction has an economic value associated with it. But why is understanding or insight important? Suppose you are able to simulate accurately, why would you bother about understanding or insight? There is a practical importance of understanding also. One is comparing models. The other is models often go wrong, and you need to know when a model is wrong, and you need to know when a model is right when you are making a forecast. And that guess cannot be made with any reasonable chance unless you have some insight into the dynamics, into the thermodynamics, and into the behavior of these models. The climate system is a complex physical system. It's inherently nonlinear. Isaac Held compared the climate science and its growth with molecular biology, which also deals with complex systems. And he noted the phenomenal progress made by molecular biology over the last half century. There's a hierarchy of biological systems. You have organisms that are very simple, say viruses or bacteria, and they range in complexity from viruses and bacteria to human beings. So there is this entire hierarchy of biological systems available to molecular biologists to study. Unfortunately, there is no hierarchy of climate systems. We have only the climate system that we experience from moment to moment. So we need to construct this hierarchy using mental constructs or models. And that is why you need a hierarchy of systems. It's not enough to have one general circulation model that you use for simulations. Apart from that, Isaac Held pointed out one more point. He said that in spite of this phenomenal diversity and hierarchy of biological systems, molecular biologists, by consensus, have chosen to work on a few. For example, E. coli and Drosophila melanogaster. This focus allows them to make comparisons between results from different laboratories. And Held points out that while we look for this hierarchy of models, we also need to build a consensus on this hierarchy that we use. The marine ecosystem is embedded in the complex physical system represented by the dynamic marine environment, and therefore it's also a complex system. There is no hierarchy of marine ecosystems, so we need to construct this hierarchy. Maybe the mesocosm, in which you carry out experiments in situ in the ocean, can provide such a tool. We still need a focus, as pointed out by Sackhild, but must keep in mind that there's a difference between the ecosystem and the climate system. In the ecosystem, the elements are adaptive. They can adapt to changes. That's not true of a climate system. It's a physical system, and the entire body of partial differential equations is available to analyze the complex physical system. So you have complex systems, you have big data and models, and through the run of science over centuries, we've had two views, two competing views. One extreme view is that the universe is in a sense a simple program running forward. This is due to Wolfram. The other is that the computer is the ruin of science and a threat to mankind. This is Truesdell's lament in 1984. There's also the question of what happens to proof as we understand it, given the kind of computational power that we have today. Now, this competition is not new. These two views have existed for centuries. The difference equations and accurate astronomical predictions predate Isaac Newton and calculus. It was the marriage of algebra and geometry by Descartes that gave rise to the Newtonian revolution. For example, look here. You see what looks like a cyclone, and this looks like broccoli. But these are not images of a cyclone or a broccoli. These are fractal drawings created by simple programs of the kind that Wolfram talks about. So what exactly are we seeing in nature? Is nature simply a program run forward in time? In this age of the chip, with Moore's law, big data, artificial intelligence, and self-learning neural networks, it's a pertinent question. Does the differential equation still matter? So this question of calculation versus deduction from axioms of first principles. The answer is that you need a mix of the two approaches. There's a practical, not merely theoretical or academic, need for insight that's provided by the differential equation and the simple models that underlie most of our understanding of science. So you need a middle path, you need the pen and the chip, and you need relevant data. To summarize, the North Indian Ocean is small, it has time-dependent wind forcing, so steady-state theories are not valid. The large-scale planetary waves propagate fast across the basin, as pointed out by Lighthill in 1969. So from the 1990s onwards, we have seen the importance of remote forcing we emphasized, and that of linear wave theory. Now in these three pictures, the regions in blue show you where linear theory can be expected to dominate. And you can see that in the Indian Ocean, except for the regime of the boundary currents, you can expect linear theory to dominate. So linear theory is still important, though the Indian Ocean is a complex physical system. It still has sufficient linearity that we must exploit. I owe a lot to a lot of people. In module 1, I showed you observations, and in module 2, I showed you the linear theoretical framework. Now, this is the past 70 years. Modules 3 and 4 look into the future. My own instinct for science, for doing science, the inspiration provided by my mentors, particularly Shetty and McCreary, and my other collaborators and colleagues, and the modest resources that were available to me for much of my research career have prompted me to take the first route. Simple models is what I have played with for much of my career. And I hope I have shown you in module 1 and 2 that this approach has its strengths. Module 3 shows that it has its limitations. But I hope module 4 will convince you that even as we aim at improving our predictions, even as we aim at improving our forecasts, we will not forget the need for understanding. Thank you.